All right, well, let's get started. My name's Chang. I work for Opower. I'm a technology lead on the data infrastructure team. So we manage the operations of Hadoop as well as build applications on top of it. And we've been working with Kiji since 2013, maybe a little. We actually started talking to you guys way earlier than that, when it was just Christoph and a couple guys. So we've been really enjoying partnering with you guys and building out our applications. So this is meant to be interactive. So I've got a list of topics proposed here, and I'm going to ask for a show of hands. I may use speaker's prerogative and pick one or two, but it's going to be a lot better if you guys ask questions. I expect to be interrupted. Otherwise, you'll be subjected to my kind of only passable handwriting. So I encourage people to chime in. And definitely want to talk about Kiji, but just also our story about HBase. So for people who are thinking about Kiji, new to HBase, we want to tell you kind of that whole story so that you can understand how we got here and arrived at the conclusion that Kiji was how we wanted to move forward. So don't shy away from asking questions that might be just about HBase as well. So I guess first of all, who's used HBase? Who has HBase experience at all? Show of hands, OK. How about HBase in production? OK, great. How about Kiji in development? Kiji in production. All right, cool. All right, that'll help me a little bit. So I do want to explain our use case because I think that's probably a bit grounding. We are a little different, I think, than some of the other use cases that WeBe Data supports, and that's been great to help sort of us as well as the Kiji platform. So the rest of these, just to call them out real quickly. So we did have an HBase deployment before we used Kiji. We learned a lot of things from that. It's one of the reasons we chose Kiji. So that's before Kiji. The learnings of that went into what we called internally Speed 2. And we'll talk offline if you want to know why we called it Speed 2. But this is basically the transition into Kiji. And we'll talk about, or potentially we can talk about the storage model. We can also talk about how we develop on Kiji. I wanted to make sure we also talked about how we deploy Kiji in production. So we've got tooling, we've got our actual sort of layout, our cluster layout and operations as a general topic, and then also just future direction. So we're in production now. We've got Kiji out there in the wild. How do we actually move forward? What are the next steps for us as Opower using Kiji? So I'm going to use a very scientific evaluation of show of hands for before Kiji. So what did life look like at Opower before we used Kiji? OK, one hand. How about how we lay out data in the Kiji world? Storage. All right, a couple there. How about how we develop on top of Kiji? All right. Tooling. OK. Production and operations. All right. And then future directions. OK, all right. So I think we'll skip this guy, and I think we'll start with the use case and then talk about storage. So choose your own adventure. OK, so I've got a very I don't even know where these came from, but anyway, that's what we do. These are sort of architecture slides, but basically we partner with utility companies to drive energy efficiency. And so what does that mean? So that means we get meter reads from utilities. That's meter read is, PG, if you're from the Northern Bay Area, PGE is your utility. We get meter reads from them. There could be monthly reads where we talk about your bill for both the usage and the cost for the past month of April. Could also be smart meter reads where we get as fine grained as 15-minute increment reads of your gas or electric usage. We get that information. We also get customer information. Information about your what's known as your parcel, your actual site, your physical location, and demographic information, as well as other data sets that we then use to join against that usage, generate insights that we deliver back to end customers, to you and me, to drive energy efficiency. So the demographic info, a lot of it tends to be from secondary data sets. some of the comparisons we do, well, some of the insights we generate are based on what's called normative comparison. And so we want to be able to compare you to people similar to you. So I guess, at a high level, I guess this is somewhat collaborative in the sense that we are looking for neighbors who are like you. And in their case, it's actually one of the factors that plays into that is, for example, geographic proximity. But square footage matters too, right? We don't want to compare, if you live in a mansion, we don't want to compare you to the bungalow, right? So all that information is used to enrich our insights that we generate. So what do those look like? Let's get a little more specific. I'll come back to that. Here's an example where we are taking a look at your historical usage, figuring out when the next bill period ends for you, and then projecting usage during that period, and also applying costs to figure out how much are you going to spend, how does that compare to what you typically spend within this bill period, and help you make decisions about that, right? So once you know this, the idea is that hopefully you might think about it. If it's more than you typically spend, maybe you'll adjust your usage, right? So that's one example of an insight. Here's another one that we are also serving off of the Kiji infrastructure, which is looking at your past 2 weeks of usage. What do your usage patterns look like? How does that compare? What are your costs, basically? So again, just informing you so that you can make decisions about energy usage. And all that goes back to this chart, which is in aggregate, this is what we save our utilities and save and through to their customers. Our general savings are somewhere between the 2 and 3% range for electricity and gas, and that's over a large population. So we currently serve, I think, a little bit north of 30 million households and drive this sort of energy efficiency. Before we came to Kiji and HBase, we and still are our relational store. We run off of MySQL. So a lot of these charts come off of our data warehouse, which has data from those MySQL stores as well as data that's being extracted from HBase. So it's this particular report was run all off of our historical stores because we're still in the process of migrating. So we started this process about a year and a half ago, 2 years ago. There will always be a place for relational stores at Opower, but certainly we're taking our largest data sets and moving them into HBase to be able to serve them out at scale. So you can sort of see one of the interesting things about our business is that it does take a little bit of time to actually see that efficiency, and that's because we're not at least historically, a lot of our communications have been batch communications, paper reports, because that's how we address the largest audience, and it takes a little bit of time for people to respond to that kind of round trip. So one of the reasons we're moving towards HBase, moving towards more real-time stores, is so that we can present those insights, potentially present them in real time, and try to close that feedback loop in the same way that you might in a retail experience, right? So, all right. So I'm going to keep that up actually. I'm going to talk a little more about what the data looks like so that we can talk about the storage model and then talk about how we use Kiji. So I imagine this in my head. It's going to be a lot less nice than when I had imagined, but let's give it a try. OK, so here's a house. This is what, in our parlance, we generally call a site. It's just a physical location where you receive your energy and use it. We have and again, in our parlance, we have a notion of what are called service points, which are really they're the meters, your gas meter and your electric meter, right? Yes, here's where it begins to fall apart. OK, so now, yes, here's the electricity coming up through here, right? Goes to the utility. This is utility, right? There we go. Coal, dirty. That's why we don't want a lot of that, right? And that usage gets stored in their own sort of data warehouses, right? They have their own systems for billing, also manages usage. These systems tend to be very oriented towards actual delivery of power, right? So that's their business. They have to keep the lights on. That's why they come to us, because they don't have a lot of expertise in analysis of that data. They don't have a lot of expertise in behavioral psychology like we do. And so when they want to figure out how do we get from here to saving energy, they start shipping that information to us from their data warehouse. And the extracts are, they depend on the utility, how we get data. But basically, we have an external format that everybody has to conform to. We ingest data, right? So largest data set here is going to be usage meter reads. We also have other information, like we talked about demographics, parcel information, that is also coming from utilities. OK, so I will talk briefly about how we did this the wrong way. In that we still have MySQL stores. So I'm going to control this here. We actually have kind of at a high level 2 of them. Because the amount of data that comes from smart meter reads is 2 to 3 orders of magnitude larger than your monthly billing. We actually, when we started integrating particularly with smart meter capable utilities about 5 or 6 years ago, effectively created a whole separate set of databases just to store AMI data. So AMI data, advanced meter infrastructure, smart meter, lots of terms for the same thing, live in one set of MySQL databases. And then we have billing data, another set of MySQL databases. Now these are in terms of the stack, we have 1 AMI database per utility, 1 billing database per utility, right? So our first attempt was to say, this is a little bit naive. We had a Hadoop experience institutionally. We had people who had worked at Yahoo. We did not have HBase experience per se. So we said, hey, look, we know MySQL. We know relational stores. We know what a tall, narrow table looks like. Let's take these tall, narrow tables that have lots of rows, and let's just basically translate them pretty literally into HBase, right? So now we've got information that's kind of living in separate tables. It actually also, we had a table, we maintained the same kind of partitioning. So we had 1 HBase table, 4 billing, 4 PG&E, 1 for the other, next utility. So we basically had, on the order of 100 of these tables, 100 of these tables. So for those of you who have HBase in production, now I'm gonna gauge you. What might, like, do you use tall narrow? How many use tall narrow? OK. So, and why didn't you use tall narrow? Or have you used tall narrow, and are you moving away from it? Just wasn't an option for you guys, or what was the rationale behind not using a tall narrow approach?
Didn't really distinguish itself from the correlation.
OK. That's true. I think for us, I'll say that one of the main challenges we had with this approach is that not only having tall narrow, but having separate tables meant that every time we wanted to do anything, and a lot of times our analysis covers both bill and smart meter, we had to always write a MapReduce job, right, just to join this data. And so that obviously incurred a lot of overhead. That's a fix on both development and operational costs every time we want to do anything. So there was that. There was also some problems we had with the actual row key structure, which I'm happy to talk about separately. But anyway, that was our first attempt. So we had been talking to
the problems with the transactions then, because you were dealing with billing data.
When you say transactions, what do you?
So transactions at a row level, since now they're at separate rows, separate tables.
We're not, in terms of, effectively reads to us, we're never writing back reads. So it's really the insights we derive off of that have any notion of transactionality. And so it would be more about data propagation that might be a problem. Like we need to have correlated time frames, right? So we want to make sure that if we need to do an analysis that includes both a bill and smart meter reads within that period, that they're correlated. And so that's not even a transaction question. It's just making sure that in this join we do that correctly. So not transaction problems per se, because we're not writing back read information. Meter reads are, to us, always read only. Yeah, that's a good question. OK, so we've been talking to folks at Weavy Data. And I think through our own experience, like we generally understood that tall narrow was not the way to go. And so The question is, though, if we're going to move to this entity-centric model, get advantages of data locality, ease of development, sort of a unified programming model, what's our entity, right? What is our, because we're not retail, we're not a customer, we do have customers, but in terms of how we model this data, it doesn't quite fit our model in that. Specifically, for example, a home, a customer is not actually tied to a home for all time, right? They move around. And so we really care about, in terms of what is our primary sort of pivot of data, energy is our bread and butter, right? And so what we decided was that we were going to take all of the meter reads and put them in a single row that was oriented by site. So let me see if I can bring that up. This is a slightly different representation of that, but this also helps you maybe gives a clearer and more legible understanding of how we laid out the column qualifiers. So we, in Kiji, you have the option to use group type column families or map type column families. Group type column families you basically declare statically. So in that you might say, well, this is the square footage of a home. If we were talking about the site being the entity, you may have other attributes that are sort of somewhat fixed. In our case, we have this kind of many-to-one relationship. So we have, in the case of a home, in the sort of degenerate case, we have very simple case. We have a gas and an electric service point, right, and energy coming from that. But that's kind of the base case. We knew that we also needed to plan for the future and be more flexible. And so, particularly with photovoltaics and electric cars and charging stations, we knew we had to be able to support many more meters from a site, right? Draw a car. There you go. All right. So, and we also we also get information about small businesses. And small businesses are a whole separate kind of beast because for a particular site, which might be a factory or could be, a rental, right, or an office space, you might have hundreds of service points. So you may have basically many, many, many columns in terms of reads. So the assumption here is that we're taking all of the reads and putting them that are related, putting them in a single column, putting those related types of reads in a single row. So does that make sense? Yes?
I missed something about your site. For this office building, is $375 rent on the site, or is it $375 on the suite?
It just depends. It probably is the entire building that's a site, is my guess. It just depends on how the utility gives us information. So, yeah. So in that case, yes, we're dealing with certainly dozens and possibly, I think we've seen some cases where we've had like 200 service points for a physical location. So.
Are you getting all the meter reads all at once? Is that why you're storing it as a single column?
No, we're not. So we get them over time. So we get these batches or this extract from the utilities data warehouses come to us on a periodic basis kind of throughout the day. And so they're just flat files that we get, and we ingest them as soon as we get them. So in this case, if we have a new bill, we just put it in this column, right? If it's a new smart meter read, we put it in this column. And to get a little deeper, I mean, these are partitioned by their fuel type too. So this would be an electric bill. This might be the electric service point. We would also have a gas bill, a gas AMI smart meter, and so on and so forth, depending on relative to the number of actual meters and service points you have at the site. So. Yeah, so basically, yeah, we're appending information into these columns. These columns are modeled as the internals of these are Avro objects that basically have the information in terms of that's relevant to that read. So it's a start time and end time and the usage at a high level. I think I mentioned we were talking about how we model this within the Kiji world. Because there's this variable number of service points, we decided to go with map type column families. So for every and I'm using the terminology we use as stream. Every stream of energy that comes into that site, we basically have a stream, map type column family, and then assign an identifier for every stream that comes in. So in this case, we would have 4 streams, and they would be labeled with the values 0, 1, 2, and 3. Right? So it's slightly different than in the sense that every row can look different. Right? Even within a utility, sites might have different service points. These identifiers are actually unique to that row. It's effectively a sequence that's per row. And so some of the access patterns are slightly different based on that decision that we made. But that really allows us to be as flexible as possible because it allows us to, as you know, again, if we encounter a case where there's more than just 4 service points or 4 streams of information, we can accommodate that. So map type column families, and then, well, we've got all this data. What are we going to do with it, right? We need to actually generate some insights and deliver those out to customers, right? So effectively, we're using Kiji MapReduce at the moment. We run that MapReduce over this row, and we produce information. We're actually using producers to produce back into that row into another column family, right? And so in this case, we've got a couple different insights. We decided, again, that we're going to, let's see, do I have a? Right, so one of these is, if we go back to this, you can see that for each of these values, or maybe you can't see, but anyway, there are costs associated with each of these bars in the graph. And for us, that's internally, we call that a rate calculation, because we're looking at usage. We're bringing in side data from the utilities that tells us about rates. We're applying those rates to that usage and then presenting that to the user. All of this is being generated off of the data in this column family on the left-hand side, right? So then we need to store it, and we store it in the right-hand side in an insights column family. And so just in the same way that we can have a variable number of streams of energy coming in, there's an equivalent variable number of insights from those streams, right? So again, we're using map type column families on the right-hand side, and the qualifier, the map type column family name is, in our case, the name of the particular insight. So we have bill forecast, we may have a rate calculation, et cetera, et cetera. So the question was, every time we generate an insight, are we generating new objects? Are we somehow updating, modifying an existing cell? In our case, we are creating new cells every time. So insights for us are a time series. If you have a forecast that we've given you today, that might change slightly tomorrow, right? We may have new meter reads in, we may have new rate information, something may have changed. So we're storing that. We generate, if we run a calculation tomorrow, we store it again. And on retrieval, we can decide based on the current time, basically what's the latest insight or what's the most appropriate insight for you, right? Yeah. And that's actually probably, that actually brings up a good point. So one of the decisions we made too, which might be slightly different than the standard Weavy data or Kiji case, is that we make pretty heavy use of the timestamp dimension in HBase as an actual logical key. And for us, again, our bread and butter is usage. That's effectively time series, right? It is a time series, and so using a logical timestamp that is tied to the read, and in our case, we tie it to the end just out of convention, that allows us sort of to easily access data, right? Because if you think about standard access patterns, we're thinking about find me a person's smart meter usage over the last month or 2 months, right? And so being able to use the timestamp as at least logical key into that data is useful. It's also very useful when we talk about aggregate analysis, right? So if I want to run analysis over our entire, this is one row, right? But we have many, many rows. If I want to run aggregate analysis across all of those, it's nice to be able to say I can set a timestamp on my initial scan and know that it captures everything, right? Because we've logically mapped those reads to an actual point in time, right? But that does create some problems just because a lot of, I think we're out of coordinates, right? So we don't have a lot of ability to resolve discrepancies necessarily. And we actually, if you saw my talk yesterday at HBaseCon, there's some edge cases where because we actually overwrite data using those same coordinates. And so that sometimes it created a couple bumps along the road that we got through with Weebydata's help. But it's definitely proven useful in terms of our actual access patterns. So it's one of those trade-offs where, we knew what we were getting into. We just needed a little help getting out of some of the holes, and we got that help. So it's different on the insight side of things. Insights, it's kind of just latest, right? So we don't, we do set the timestamp, but it's more just that's when we perform the calculation. It's effectively usually the same as wall time. Now, it also happens that we do have, we do use separate H-based column families for our different use cases. So similar to what Amit showed, our reads are generally accessed, well, they're read-only. They're generally accessed in mostly batch patterns. So we have a column family there that has is more about disk oriented in terms of how it's laid out. And then because these insights are actually served out in real time, those have they're actually they have more memory characteristics in terms of the underlying physical storage. So okay. That's storage. Any other questions about the way we've laid out data? Yes.
So if I'm interested in just like the billing data or just the electric reads, and now I have streams indexed by 0, 1, how do I find which is which?
Yeah, and so one thing that's not shown anywhere here, is that we have another column in this row. And this is a group type column, which is effectively a metadata column. And metadata meaning it contains information about if I am interrogating this row and I want to find an electric service point with an external identifier provided by the utility company. So we always have some external identifier that's provided to us. How do I know where that information lives in this row? And so I always have to pull this particular cell or column, right? Look up by, let's just call it service point ID. That's something from the utility. It's an external ID. There's then a structure in here. It's just an Avro object as well. It's basically a map that tells me, oh, OK, well, you're looking for that particular service point. It happens to be and again, these are the actual names, right? It actually happens to be this column, right? So that's the trade-off for using a map type column family, in that in the way we've laid it out, our identifiers are dynamically generated per row. So we always have this sort of requirement that before you figure out what you want, you need to interrogate this particular column.
Because it might change by row.
Yeah, exactly. And so a couple things about the nature of our business. So in addition to having variations across sites, a site actually could evolve over time. So particularly for utilities that are deploying smart meters, we might start by just getting billing data. And then all of a sudden, as they start onboarding smart meters, we'll get another stream, which is the AMI stream, right? And so depending on the order of that, there's no consistent ordering you can rely on for a particular row. And we don't really want to rebuild all our rows every time a new stream comes in just for consistency, right? At one point, we had thought about, well, could we use a group type column family and just create enough buckets? But we sort of backed out of that because it would be hard to sort of reason about that, right? Like, there's still not a notion of like, is this, like, what's this electric smart meter bucket? How's that different from the second one? They're all, you sort of need to have some context that's specific to that row. It's a good question. So why didn't we use the external ID? It really is based on size. There's a size requirement. So these can be, I think, these IDs from the utility companies can be up to 50 bytes. And because we're using map type column families, we don't get the Kiji advantage of minifying this column. They'll minify the column family, but the actual qualifier will be whatever you set it to be, right?
Did that with the prefix encoding?
There is some of that, and we did some testing on that. We didn't see that much benefit from it, particularly because these are pretty different, right? So yeah, this is a good question though. So yeah, so that is why we have to do this additional lookup, right? We've made different decisions, actually, so that's a good point. We did make different decisions on the insights. It really depends on the insight type, but insights are often groupings of information for a service point. And so in that case, we actually do set the qualifier to be the service point, but that's because the cardinality of insights is much, much lower. So we might have, I mean, by 2 or 3 orders of magnitude. And so one of the things that bit us in our first iteration is that we didn't realize HBase was storing its row and key values with every single cell. So we could make decisions now that we knew that in terms of where we would use, we would be okay with larger keys and where we would want to use smaller, qualifiers versus other cases. So, right. So the question is, why didn't Kiji take care of this for us? It's because it's specific to map type column families. So with group type column families, if you think if we imagine how Kiji does things out on the covers, it's static, right? So it can introspect a schema and decide, oh, I've got 10 group types, right? I can assign sequences to those, and there's actually tables that support that. With map type column families, where you have a variable qualifier, it can't make that decision ahead of time, right? So if it is one thing to look at. If you're going to use map type column families, you should be aware that the final qualifier you assign is going to be represented raw. Now the column family will be minified. So this is still going to, what this will look like in HBase, it'll be A0, B0, or B1, right? Actually, sorry, that should still be A because they're, nope, different column family. Sorry. So yeah, A0 and nope, same column family. These are electric, right? Yeah. So right. So it's the second part that you'll need to be aware of. The map type, sorry, is for map types it aliases the first part. So when in the Kiji DDL, you will say map type column family with name, and we call the map type column family stream, but that gets minified. The actual final part of the column qualifier is not minified. So I mentioned that we're using logical timestamps for our read stream, our streams of energy, right? So if we draw kind of a timeline here. So this is today. And let's say we've got a bunch of reads that are, let's say we have our stream 0 kind of is there. And our stream 1, let's say, has some overlap. And it's here. So I still need to store the metadata somewhere, right? But how do I store it in a way that I can guarantee I can efficiently pull it in when I need to? So if it's at an arbitrary point in time, right? If it's in the middle of these streams, or let's say I imported this site 2 years ago, right? And now I'm looking at more recent reads. So this is when we actually received the site. Tying ourselves to timestamps here kind of makes this a little awkward, right? So how do I both grab this and this, right? Without having to scan the entire row every single time. Because if I don't have a notion of how this relates to my streams, I don't know how to make that query, right? So another trade-off here. So what we decided was that we would use what we've called internally time shifting. And when we pull this record in, we push it forward by 50,000 years. Okay? So it's not quite a Y2K problem. But so in fact, the site lives up here. So site metadata. This is not to scale, obviously. Sorry. OK, so right, so now it's there. So we still have to grab it, though, right? And so there's still a question of access patterns. And what we decided was this was OK, because most of our queries, if you think about today, are looking backwards, right? A certain amount of time, a month, a year, whatever that is. there's a general assumption that there's not too much data after today. I mean, hopefully we're mostly in current time and not getting future reads from sites. If utilities, it happens sometimes. It's data and we get it, but generally not too much data here. So what we actually do is we say, okay, every time we think about a query, this is our initial query, but then we bump this up by basically the end of time, right? So effectively, it's open-ended, right? We just say start here, end, HBase timestamp, end of time, right? So we pull all these guys in, but we cut off anything. If this is where our query begins, we're still omitting stream data from before that, and we're also picking up, well, this site metadata. Yeah. So this is great. We've got everything in one row. We have a way to evolve over time to be flexible about not only just the number of service points and streams of energy on a per row basis, but in general in our domain, like as we start bringing in new types of energy, measurements of energy, thermostats is another example where that's a time series of information, right? How do we bring that into this model? Now we have a way to say, okay, we've got a common pattern where the mapping, the actual navigation within the rows is in one place. I can go there, look for it. I know how to get to it because it's in the future. And it will always help me navigate to where I need to get to do my analysis, right? OK, so development. Unless other questions about the model? And I'm not keeping track of time, so we'll just, we'll just end on the end, I guess. But by whatever content we cover in the time allotted, we'll just stop there. So, and we can talk about, feel free to come back later and ask questions somewhere. Right, so I mentioned that in terms of processing, we're running MapReduce over rows, producing into columns. Again, we're actually using the Kiji producer, right, which is what you use to write back to a row. Somewhere I had this is a kind of dense slide, so I'll wave my hands a bit, and then we'll dive in if there are questions. So this should look familiar. This is the site table, right? We have the metadata column, right, which tells me how to get to these particular columns that actually contain the data. There's a process by which, though, we populate this table. And a lot of it is again, specific to our domain, but it's about getting data into this form. And so I mentioned we get flat files from utility companies of meter reads. We actually ingest them into a log. And there's a couple of reasons for that. One is that we want to be able to decouple the process of ingesting reads from getting to their final home in the site table, because information comes to us at different frequencies. So we may not actually get a site at the same time that we get reads. There's always a little bit of kind of initial launch with utilities where we may not have a one-to-one for all of these. The other thing is that it's just nice to have a place where we can have this data audited. And the other thing is, I mentioned we sometimes overwrite reads. We use a different timestamp scheme in here that is purely based on when we receive the reads so that we can differentiate, right? So if we get a read and then that same read 2 months later with a correction, both those entries will still live here. They'll get resolved into one read here, but this gives us the ability to go back and understand how we got there. So the first set of jobs takes these flat files, ingests them into, there's one read log per type of data. So we are currently kind of importing data, again, sort of based on how they're delivered. So we get one set of bill reads and one set of AMI reads from utilities, right? Separately, we have a job that, and I mentioned MySQL, right? That's always going to be there for us. We need to populate this metadata column, right? What are the relationships between, I lost it, a site and its service points, right? A site and its streams. So independently from these jobs, we're running a job that basically runs a DB input format out of MySQL on a periodic basis, pulls our relationships of sites to service points, which we translate in our parlance to streams, and creates this mapping. It doesn't populate these columns because the columns don't exist until they have data, but it reserves space for them in the sense that the map that is maintained in this metadata gets updated, right? So if we detect that we have 2 service points for a site, we'll create 4 streams, right? One for each billing and AMI, and then for each of those service points, store that in this map. At which time we get reads for those particular service points, that's when we'll be able to assign cells, and columns really only exist if cells are there, right? So we've reserved the space here. So we're populating this table. Somehow we need to get the data from these read logs into this site. So if you think about it, we're taking, well, I guess I should explain a bit more. The read log, the entity for the read log is not actually the site. It's different because the information we get is really by service point. They're giving us information that these are your gas meter reads. Yeah. 5 minutes? OK. And these are your electric meter reads. So our entity here is actually the service point. So what we need to do is effectively take a row here and pivot it into a column, right? Because this is a site. A site has many service points, one service point per entity here. So there's a pivot here. The one thing I want to call out, the reason I wanted to call that out is because the way we're doing that is as we pull information from MySQL, we also populate a side table that has that mapping of service points to sites. And we expose that through a key value store, which is another Kiji construct. So that allows us to say, OK, as we're mapping over these reads, what row do I need to target, right? And oh, by the way, now that I can get to the row, I can interrogate the metadata, figure out which column I want to write to, right, in that map type column family, and then import those reads into that map type column family, right? So that's this job, which I won't, it's got a long name, but it pivots bit data basically. Yeah, and that point basically, we're basically doing what we had talked about before. So now we've got our data in the site table, our main entity table, and we're running our our calculations, our insights. Sometimes we're pulling information still from MySQL, right, in the form of rates, for example. Using that in the job itself, there's a good amount of caching that happens there to make sure that we're not slamming our MySQL instances. Enrich the data and store that back into the same row, new column. Right. Questions? Yes.
Why aren't you using a distributed cache to bring that data around instead of caching it?
A distributed cache for the data retrieved from MySQL? It's just enough information. So depending on the size of the utility, so let me take a step back. We're running a single map reduce job over every utility, every row in this table for a particular utility. So this table does contain data for multiple utilities, but we're still, for any one calculation, any one map reduce job, picking up all rows for that utility. That being said, we don't actually know ahead of time what service points or what sites are going to be visited. So I mean, I suppose we could take the entire contents of the table and tables and put them into distributed cache. I mean, that could be an option. I think we decided a lot of this is about how do we evolve from something that was purely MySQL into a MapReduce world. And we found that for these random access lookups that are cached, that we get fine performance. So the complexity of having to take something that's in MySQL, put in distributed cache wasn't really necessary in our case. But we would have to, because we don't know what sites we're visiting, we would have to take the entire MySQL table and put it in the distributed cache. It probably would fit, but it might not. So we have utilities with tens of millions of sites. And so can that fit into a distributed cache and also be pulled into memory in a meaningful way, right? That's the other part of it. Unclear. The nice thing is that if we ever decided to go that way, the key value store is a nice abstraction that can sit on top of the distributed cache. We could leverage that pattern. So yeah, I mean, a lot of it is just that this is legacy. One of the things I should mention is we're dealing with code that's from our legacy code base that is before really ran off of MySQL. We didn't want to rewrite all of that, and so we wanted to try to reuse what we had. In some places, we could replace our access to, we decided we could replace our access to use Kiji's data sort of access layer. But in other cases, we just had to make a sort of prioritized decision on where we get that data. So we kept it in MySQL. Yes?
How big is your cluster and what's your data size?
So overall, between our data warehouse and our serving clusters, we have a couple dozen nodes. Our overall data set is, I mean, those are, it's compressed and everything. So I mean, compressed, it's around 100 terabytes raw. So 3x replication. So yeah, it's on that order. So yes.
So knowing what you know now, if you design this again, would you still use the timestamps the way you do?
I think so. I mean, the other advantage of timestamps for us is that it allows us to, in addition to having sort of accommodating our access patterns, it also allows us to be relatively idempotent, right? If we need to re-import reads, let's say we have a failure, right? Or let's say a utility said, hey, you know what? I screwed up everything. Like everything was wrong with this particular import, right? And we had a bit flag set improperly. Everything's shifted by a day. Or sorry, the usage values were shifted. Something was wrong about them. It's very easy for us to know that those reads will go into the place we want them to because we know that the timestamp is a logical key. Okay, I think time's up. Feel free to ping me if you have any questions. Got some of my colleagues around here too, so thanks for your time.